Okay, so what we're looking at today is buoyancy and how it relates to specific gravity. So in this case, we're looking to derive an expression for specific gravity for when h is greater than r. So we're looking at basically a cylinder that's floating like a log on its side in a river, and we're looking to derive that expression of the log as a function of h over r. So to start, we're just gonna look at a diagram. So basically, what the log would look like with that center point with the radius of r, and if this line is where the water level is, then the space between that top part of the cylinder and the water level is going to be defined as h. And then anything that's under here is the cross-sectional area, and that's below the water level. So another way is also to look at it from the side, and therefore to look at it this way, it gives you a better definition of what that length L would be. Same thing from here. You have that radius in the middle. And so we're going to start with some basic equations to substitute into the final equations to get to terms of h over r. So to start, you're looking at W, which is the weight of the water displaced, and we know that that's equal to mass times a gravitational constant. So gravitational due to acceleration due to gravity. And we also know that in this case, density is equal to mass over volume, or if you're solving for mass in this case, it's equal to density times volume. So you can substitute that in to this weight of water displaced equation. So now you have density times volume times gravity. And if you're looking at the volume of a cylinder, that V, which is going to be able to be substituted into the above equation, is equal to pi r squared. And in this case, it's technically height, but we're going to use that length L. And substituting this V up here, you get that density times pi r squared. Remember, r is equal to that radius times the height L times the gravitational constant G. And then we're going to, from these equations over here, we're going to get that the density of water. So the rho W is water, and then on the other side, rho L is density of log. So then we have area times the height times gravitational constant equals rho L, so density of the log, times pi r squared height gravitational constant. And as you can see, the L's on both sides and the G's on both sides are going to cancel, leaving us with just these parts here, which will be substituted later. But first we're going to look at another diagram here. So it's basically what we're looking at above with the circle here, but we're going to add some aspects to it. So you still have this water line here, but in this case, the center, we're going to attach these radii to the corners, and this height is still going to be h here. But now, since this forms two right triangles here, we're going to call this height that's between it r minus h. And now you have these right triangles, the bases of them, we're just going to call them B for now. And then this inner angle here, technically on both, considered theta. So when you're looking, we can start just by solving for the bases here to understand the triangles a little better. So you have b squared. In this case, you're using Pythagorean's theorem. So you just have some r squared minus r minus h. Sorry, I wrote that square root prematurely because you're basically just square rooting both sides, which ends up giving you square root of 2 RH minus h squared after you do the algebra, and since it's two triangles, it would actually be 2. And so now let's look at theta. So all of these equations are going to be substituted in to help to get the final one, but we're going to do them all a little bit separately at first. So when you're looking at theta, just from trig, from right triangles from high school, we know that cosine of theta is equal to r over h, r minus h over r, which is the hypotenuse. And then if you take the inverse of that, you can find what theta is equal to. So cosine -1 r minus h over r. And now we can start looking at some of the areas of the shapes here. So if you're looking at the kind of cone figure, we know that the area of that is going to be, we'll call that 2 theta over 2 pi, and that's multiplied by pi r squared. It's theta. And now that we know this value of theta, we can actually plug it in. So that's going to be simplified down, r squared cosine -1 r minus h over r. And for the area of the triangles, you know that the area of a triangle is 1/2 base times height, but in this case we have 1/2, and then the base that we solved for over here is 2rh minus h squared, and the height is r minus h, but this 1/2 and the 2 are going to cancel, just so it leaves you with that. And then if you're looking for just the top part of the cylinder, it's just the cone minus the triangle. So it's going to be these two values. So r squared cosine -1 r minus h over r minus the quantity 2rh minus h squared times r minus h. That's like this. And so if you're looking for the underside there, that's r squared, because you know that the area of a circle is pi r squared. You have pi r squared minus the top part. So we're going to start on a new sheet of paper for this next part. So the last part what we're doing here is we're just plugging in all of the areas that we had solved for previously on the other page into the first equation that we found, which was the density of the water times the area equals the density of a log times pi r squared. So basically what we're doing now is just plugging in the areas that we solved for. So we have the density of the water, it's going to be multiplied by pi r squared minus r squared cosine -1 of r minus h over r, and that's going to be the cone. And then we have the triangles here, which is square root of 2rh minus h squared times r minus h, and that's equal to the right hand side, so it's the density, that's equal, of the log times pi r squared. And then to get it in terms of just the right hand side of the density of the log by itself, you just divide all the way through by pi r squared on both sides. And then that is going to get you density of the water is 1 minus 1 over pi cosine -1 of 1 minus h over r minus 1 over pi r squared times quantity r squared, and that's multiplied by 2 times h over r minus h over r squared times 1 minus h over r. And that's equal to that right hand side. And then in this case we know that specific gravity is equal to the density of the log over the density of the water. So it's helpful in this case to put it in terms of h over r, so when you get those values, this last equation, you can just plug them straight in. So for this second part here, we're setting up a calculation using code to calculate h over r for a cylinder with specific gravity of 0.8. So now we have a specific number, and we're just going to be looking at the equation that we derived in the first part. So we are going to import numpy as NP, so we have our library of functions, and this is from optimize, and that's importing root scalar. Also, in this case, we don't technically need a plot, but I think it's more visually understanding to see it. So graph objects as go, and for the last part of the plot here, we're going to import plotly IO as PO. And on the second part, this is where we're actually using the equation that we derived in the first part. So first define H over R as NP. That's from the number from above, when space. Now we have 0, 1, 10. Close that. And specific gravity here is our actual equation, 1 minus NP dot arc cosine, which is, as we know, inverse cosine 1 minus HR. Oops, right there. And then we have minus NP dot. So now we have the square root function of 2 times HR, and that is minus HR squared. And that's times 1 minus HR, and that's all over numpy. Basically bringing the function in. So for this third part here, which is going to be focusing on the graph, which again, not necessary, but I just think it is more, it's easier to understand when you see it visually as well. So to start, we have figure equals O dot figure, close brackets there, fig dot add scatter. And this is when we're looking at x is equal to that HR value, and the y is equal to the specific gravity value. And now we have fig update underscore layout, talking about the template equals Pio templates plural, and then that's going to be in brackets of plotly, dark, close both of those, and then we have the fig dot up layout again. This time to show the height value at 400 and width. Apologies for my terrible typing skills. And now we have title. So x-axis title will be equal to H over R, and the y-axis title is equal to specific gravity. The x-axis underscore 0 equals 0 in this case, and the last one here underscore is at the value 0.2. Now we have the title of basically what the whole graph is going to say, which in this case we're going to call it specific gravity of floating cylinder for, and then this here is going to break that line so that it's easier to read the title when you're looking at it. Varying height H, and so that it fits in the whole screen when you're looking at the graph itself. Above water level. And then the last part here is just setting that title equal to 0.5.
and close out those, except for this last should be there. And basically what we're going to do from here is just go ahead and run all. So what you're going to see is the graph that we have just made above, and then to return out the part from the equation, we are going to define HR function and return this equation from here, which I'm just going to copy so we don't have to take the time to rewrite it all. And that's going to be, except for this time, the whole thing is in parentheses because we're running the value at 0.8. And now we have to get the result. We're going to do that root scalar function. And then we have f bracket, and that's equal to 0, 1. Close that out. Result one more time. And apologies, I forgot to add the colon there to specifically define, but I added it now, so when we run all this time, you are going to see the result, and this is the result answer.